Thank you, Kim. Thank you, everybody. And I just want to reinforce something that Kim said. I've been here several times with different topics. So this particular program has to do with pulsar timing arrays that I'm going to talk about today. I've been here for cosmology, or early universe cosmology, and other topics as well. So it really has been one of the most productive and exciting places to do physics. So again, thank you for your hospitality. That's so true. Okay, so I'm going to talk about this galactic-sized gravitational wave detector and focus on the physics and astrophysics of pulsar timing arrays. So to get us started, I'm going to talk a little bit about discovery of gravitational waves and just some bullet points of things that I'm going to cover over the next 45 minutes or so. So there's some really interesting kind of human aspects to the kind of physics that we're talking about today, gravitational waves. They were predicted by, essentially, within Einstein's theory of general relativity in 1915, and it took 100 years for us to directly measure them. We're going to talk a bit about that extremely exciting first measurement. And in doing that, I'm going to address these questions. So what are gravitational waves? What do they do? And where do they come from? At least the ones that we've measured so far. And I'm going to also address why this discovery is so important. What do we actually know now that we didn't know before? And this galactic-sized gravitational wave detector really fits into this last bullet point here. We're at the cusp of something extremely exciting in terms of the future of measuring gravitational waves. So I'm going to focus on that in the last part of the talk and where we go from here. So to get us started, I'm going to talk about a very, very famous thought experiment that Einstein came up with in order to think about gravity in a way that's completely different than how, if you've taken physics in high school, than how you learned from the perspective of Newton. So I'm a theoretician. I don't usually do demos, so excuse me if this doesn't work, but I have a little demo here. And I encourage you, I'm going to ask you to imagine some things in a moment, and I encourage you to really try to imagine what I'm describing. So Newton has a very particular perspective on what gravity is. It's a force. So the mass of the Earth exerts a force on the soccer ball, and when I let go of it, that force pulls the soccer ball down to the ground, and it falls to the ground. What Einstein realized is that we could take a completely different perspective of this situation. And instead of thinking about gravity as a force, we can actually, when I take the soccer ball and let it go, we can imagine and really try to imagine this. The soccer ball remains fixed in space, and it's actually the floor that is rushing up and us rushing up to meet it. So let's see if that feels any different. This is going to remain fixed, but we're going to rush up and meet it. I felt a little difference there, and I hope you did too. So from this really simple and profound idea, this thought experiment, Einstein revolutionized our understanding of what gravity is. So one way to understand that, if we think about like the Earth orbiting the sun, Newton tells us, again, there's this force of gravity that's causing the Earth to orbit around. But space-time, from the perspective of Einstein, starting with that thought experiment, becomes dynamical. So it's not just a stage upon which things happen, but it becomes part of the drama. So I want to talk about some of the first tests of Einstein's ideas. They actually happened very soon after he put forth his theory of general relativity in 1915. One of his first papers talks about how his new theory of gravity can explain the strange aspects of the orbit of Mercury. He also predicted that light would follow a curved path around the sun. So when I think about this test, some of you might have seen this before, but this is a news clipping discussing, this is really what made Einstein internationally famous, that the lights were all askew in the heavens. So light, because of this dynamical space-time, bends around the sun. And there was a measurement in 1919 and says that Einstein's theory triumphs. And I really love this last part here, a book for 12 wise men. So general relativity is so complicated, only 12 people in the world could understand it in 1919. Not true, but it gets people to read. the article. No more in the world could comprehend it, said Einstein, when his daring publishers accepted it. So, not very good business people, but they published it and we're grateful for it. So, as I said, along with these tests, contained within Einstein's theory of general relativity is the prediction of gravitational waves. So I want to discuss some of their properties. Okay. So some of this language is a little technical. I'm going to describe what it means. So gravitational waves are transverse. What that means is that the action of a gravitational wave occurs perpendicular to the direction in which it's moving. And Einstein's theory also predicts that it moves at the speed of light. So the action of this gravitational wave is to stretch and squeeze space-time in the way that I have drawn here. So if we imagine at the wave crest, this gravitational wave is pushing down in vertical direction and stretching out in the horizontal, and this alternates pattern over and over again. So to visualize this, we can imagine dropping a pebble into a pond. This is sometimes used as an analogy. And if we did that, if we had a boat sitting on the pond, that boat is just going to move up and down. So this animation shows that. But if we had a boat and we had a gravitational wave coming out of the screen, that boat is going to stretch and squeeze, as I described before. So we're using the stretching and squeezing in order to measure the effects of gravitational waves. So as I said, in 2015, it was one of the most, actually for me, the most exciting discovery of something in my scientific career. Gravitational waves, 100 years after they're predicted, are measured by the LIGO observatory, and I'll talk a bit about what that is. So what do gravitational waves do? So there are two ways of unpacking this question. One is saying, what's happening at the source of the gravitational waves? What's producing those gravitational waves? And then what does the gravitational wave do when it reaches our detector? At the source, gravitational waves carry away a lot of energy and information about what's going on at that source. And as I'm going to emphasize a few times, at the detector, gravitational waves have an extremely small effect. Very difficult to measure. It is because gravity is such a weak force. You might have heard that before, but I want to use this ball as a demonstration of that again. The entire Earth is pulling down on this ball, and yet I can lift it up and counteract that pull. So this is a way of understanding gravity is so weak. I can overcome the action of the entire Earth. So at the source, typically we're thinking about sources of gravitational waves as objects that are orbiting one another. As they orbit, the gravitational waves leave the system, and energy is carried away, causing those objects to move closer together. And as they move closer together, just like an ice skater, when they pull their arms in, start spinning faster, they orbit faster, and then at some point, they collide together. So at the detector, I'm going to discuss a particular type of detector. So this is the detector that was used for the first measurement of gravitational waves, and it's called an interferometer. So in a moment, I'm going to play an animation, and I want to describe the various elements that we see here in the animation. So here in the cylinder, we have a laser. The laser light is going to leave that cylinder, and it's going to encounter what looks like just a line here. This is called a beam splitter. So half of the light is going to go to the left, and half of the light is going to go straight ahead. Those black circles are mirrors, and as the light hits those mirrors and reflects back, they're going to come to this square and combine together to either produce light or dark, have no light come out. So let me show you the animation in all of its glory. So there's the laser light, and a gravitational wave is passing by, causing the lengths of these two arms of the interferometer to change. And what's happening is we're using the effects of destructive and constructive interference. So, in the absence of gravitational waves, the two arms of the interferometer produce light that destructively interfere. But if a gravitational wave passes by, you get possibly some constructive alternating with destructive interference. And what we're measuring is this alternating light and dark in detecting these gravitational waves. So as I said before, gravitational waves have a very, very small effect at the detector. And to give you some sense of how small, for the LIGO detectors, they are actually monitoring. They can measure shifts in the change in the distance along those two arms of the interferometer, 1/1000th the size of a proton. So you can imagine, this is why it took 100 years for us to actually measure gravitational waves. So many technological advances needed to be made and understood in order for us to actually do this. So to dig a little deeper into this first detection, this is actually a figure from the first detection in 2015. So let me unpack it for you. On the top here is a cartoon showing us two black holes whose gravitational waves we measured. Each of these black holes are 10 or 20 times the mass of the sun. So these are extremely massive objects from our perspective. They're orbiting each other, emitting gravitational waves. This middle panel here shows us the alternating light and dark that's measured coming out of the interferometer. On the bottom here, we're getting some quantifying two things about the orbit of these black holes. The black curve here shows us the black hole separation. I would not expect that to be of interest in general. The green curve, though, is something that I really want you to focus on. The green curve is showing us the relative velocity of these black holes in terms of the speed of light. So as we're watching the gravitational waves coming from the system, as we're getting information about this system, we're actually getting information about objects that are 10 times the mass of the sun, moving relative to each other at half the speed of light. So that is an extreme event. And there are aspects of that before we make this measurement, we do not know what's going to happen. It's a realm of nature that we never had direct information about before. So, closing up the discussion a little bit about these gravitational wave detectors on the Earth, I want to point out that there are now a handful of gravitational wave detectors on the Earth, which are making these measurements, and they combine their efforts together. And this is a summary plot of, in some sense, the key thing that we learn from these measurements. So this is called masses in the stellar graveyard. These black holes that we're measuring with these interferometers are typically thought to be the end life of a very massive star. And what we're seeing are these black holes typically coming together, merging and forming a slightly more massive black hole. So each of these blue dots is a black hole that was discovered by these interferometers. And you can see that there are two of them with an arrow telling us what they became after they merged. There are things about this that we expected, and it agrees with what we expect. There are things about this that are unexpected, and we're still trying to figure it out. So this measurement of gravitational waves occurs at a very specific wave period. And gravitational waves, just like the light that you're using to see around you right now, come in a spectrum. You can have gravitational waves all the way down here that are millisecond period, and that's what these interferometers are measuring. We can imagine gravitational waves that have periods as long as the age of the universe. And just like we have radio dishes in order to measure radio frequency electromagnetic radiation, there are different techniques that we use in order to try and measure gravitational waves at different periods. So along with these different periods for the gravitational waves, we have different sources. These terrestrial interferometers tell us something about, well, this is a hope that we might learn something about neutron stars and supernovae, but the thing that these detectors have measured a lot of are what are called compact binaries in our galaxy and beyond. If we look at these other detectors, I'm not going to talk too much about this, but we can put an interferometer in space. So this is something that is maybe 10 years away. And then we have pulsar timing that tells us something about gravitational waves with periods of years. So if we look up here in terms of sources of gravitational waves, there are very different sources than what we measure with the interferometers. We measure what are called supermassive binary black holes in galactic nuclei. I want to talk about that. So before I do, I want to talk a little bit about what these PTAs are. Pulsars are natural clocks. They are rapidly rotating neutron stars. And I remember actually being here a few years ago and having someone give a colloquium about PTAs, and it made a very important point. Neutron stars are fascinating in their own right. There are people who study the physics of neutron stars. That is not me. That is not the people who are using these neutron stars in order to measure gravitational waves. They, for us, are essentially clocks. And you can visualize what they're doing. They're like lighthouses spread throughout the galaxy. There's light coming out of two poles for these neutron stars. Every time that spot of light passes by us, we see a pulse. It's exactly like a lighthouse. And we're specifically interested in a subset of these pulsars that have very rapid periods, 1 millisecond to 30 milliseconds. These pulsars themselves are 10 kilometers across. So we're talking about objects that weigh or have a mass as large as the sun, size of 10 kilometers, and they're rotating at about 1 millisecond to 30 milliseconds each rotation. And the reason that we need these very precise clocks, come back to the fact that gravitational waves have very small effects. The typical gravitational wave causes a drift in the arrival time of 100 nanoseconds over 10 years. So a very, very small shift in the arrival time of these pulses in order for us to actually measure these gravitational waves. So to give you a visual sense of when I say this is a galactic-sized gravitational wave detector, I'm going to put these pulsars onto an image of a galaxy. Now we don't have an image of the Milky Way, right? We can't zoom out and take a picture of that. So this is some other galaxy, but the Milky Way is a spiral galaxy, so it looks something like this. And you can place these pulsars, so these different lines here correspond to the spiral arms of the Milky Way, and the pulsars that we're using are in the blue dots. To give you a sense of how large of a space these pulsars take up, the distance between us, we're a little black circle in the middle there, and the center of the galaxy is 26,000 light years. So these pulsars, these clocks, these nature-made clocks that we're using to measure gravitational waves are spread over thousands to tens of thousands of light years in the galaxy. And the image that I want you to have in your minds is, as we have sources of gravitational waves, which I'll talk about in a minute, they produce these waves that wash over the galaxy. So this is a very fancy animation that I made for us to imagine that. There's a gravitational wave that washed over. We've got another one. They're coming from all sorts of different directions. And the key thing is, how do we use this? How do we take the information that we gather, these clocks, and infer the presence of these gravitational waves? Sources of these gravitational waves, as I said before, are thought to be binary supermassive black holes. So let me go into that a little bit. get us started, I want to show you something that for me, every time I see this movie, it gives me chills. So this is an image, this is going to be a movie in a moment, of stars towards the center of our galaxy that were measured by a group at UCLA led by Andrea Ghez. What they did is they looked at these stars over about 15 years, measured where they are, like very, very basic measurement. And so they can track the orbits of these stars over those 15 years. So we're gonna see that unfold now. So there are the stars moving, and you can see that for some of them, they've given us a visual aid by showing us the path that they're taking about the star, this symbol of a star. And just like the way that we measure the mass of the sun, we can measure these orbits of these stars and figure out the mass of whatever object they're orbiting about. And it turns out that when you do that, you find out that this object is 4 million times the mass of the sun. There's no visible light coming from it. So the simplest interpretation is that we are seeing these stars orbit a black hole, a supermassive black hole, at the center of our galaxy. Just to say, I mean, Andrea Ghez, along with others, won the Nobel Prize for this not too long ago. You might also be familiar with another kind of direct measurement of a black hole that was in the news not too long ago. And this came from the Event Horizon Telescope. So there's a galaxy called M87, and this group took radio measurements of the center of this galaxy and produced this image. And this dark region here is the event horizon, the surface of the black hole that's at the center of this galaxy. You can use various ways of estimating the mass of that black hole. This black hole is 6.5 billion times the mass of the sun. So 4 million for our galaxy, 6.5 billion here. I do want to say something. Even though these are large masses, these are small objects. You don't have to worry. The black hole at the center of our galaxy is very far away and very small. It has no effect on us. But this is giving us direct evidence that these supermassive black holes exist. And when galaxies collide, we get binary black holes. So galaxies are colliding throughout the universe all of the time. And there's evidence that there are these supermassive black holes at the centers of all of these galaxies. And over time, after galaxies collide, those black holes settle down to the center and start orbiting one another. And that provides us with the source of gravitational waves that we are potentially measuring with pulsar timing arrays. So to zoom out even farther, so I showed you an image of our galaxy. Now I'm talking about the sources of these gravitational waves we have. Zooming out even farther, merging galaxies fill the universe around us. So this is an image from a simulation. So this is not something that we have, it's not an actual observation, but this is a simulation of a large volume of the universe. And what we're seeing in these different colors is the density of matter in various locations in this simulation. The brighter locations are more dense, the darker locations are less dense. At these bright nodes, that's where a lot of galaxies reside. And those galaxies are dynamical. They are, over cosmic time, finding one another with gravitational interactions, merging, and then, as I said, their supermassive black holes eventually find one another, and they also will merge. This is a crazy number. So this simulation, this length scale here, I would not expect that number to make much sense, but to make it make sense, the entirety of our galaxy is 1/10,000th the size of that bar. So we reside somewhere in here, even smaller than a pixel on the screen, and we're surrounded by all of this unbelievable structure in the universe, potentially producing gravitational waves we hope to measure with pulsar timing arrays. So let's see. Oh, all of those black holes are orbiting, and they're going to merge. Oh, that's exciting. So pulsar timing arrays are, the term itself refers to a collection, a set of data that we take as we monitor pulsars in our galaxy. And there are different groups that do this around the world. So just like the laser, the interferometers that I talked about before, very international effort, pulsar timing arrays are also extremely international. So I'm an associate member of this group here, Nanograv, that has members in North America, or really telescopes in North America, radio telescopes. Very unfortunately, Arecibo, which was one of the premier telescopes that we used in Puerto Rico, fell apart, and we no longer have that telescope. It's not going to be rebuilt. But there are other radio telescopes that are being built. One in particular is FAST in China. So there's a group, the Chinese Pulsar Timing Array, that uses that telescope. There's a group in Europe, the European Pulsar Timing Array, one in South Africa, Meerkat, and one in India. So these efforts, another thing to keep in mind, I mean, I guess something I can say is that gravity is very weak. Therefore, any experiment takes a long time to actually measure something interesting. So these efforts, in the case of Nanograv, this has been ongoing for more than 15 years. In the case of the European Pulsar Timing Array, it's been something more like 25 or 30 years. The Meerkat and the CPTA are newcomers. They've been taking measurements for the past few years. And Parkes has also been going on for 10 plus years. So 2 years ago, there was an amazing announcement made that the cosmos is thrumming with gravitational waves, astronomers find. Radio telescopes around the world picked up a telltale hum reverberating across the cosmos, most likely from supermassive black holes merging in the early universe. This was an extremely, obviously, very exciting announcement. I had been part of Nanograv for several years. I do want to highlight that if you are interested in science journalism, I find Katrina Miller to be one of my favorite writers. She, at this time, 2 years ago, was a new journalist at the New York Times and has continued to write with them. So I want to give you a sense of what the actual evidence looks like from the perspective of someone who works in the field. So this is going to be much more technical than anything else I've shown. We have two different plots here that combined together give us some sense of how confident we should be that we've actually measured something, that this announcement 2 years ago is going to be correct. So on this left plot, what we're seeing here is the excess timing delay. So this is the timing delay in the arrival of those pulses that will be affected by gravitational waves. And these gray curves here, if they pinch off, there is some significant evidence that we've measured something that's non-zero, which could be the effect of a gravitational wave. You can see that in principle, the measurements that we make with the PTA could measure this many, many times over. But once we get to around the fourth or fifth of these, and this is a function of frequency of the gravitational wave, we find that the evidence drops off. So we have evidence at these lower frequencies, then the evidence becomes weaker as we go to higher frequencies. This is something that we expect. So it's not unexpected, but it's something to keep in mind. More important quantity is over here. So I'm going to use some technical language for those of you who might find it useful. When we're looking for the effects of gravitational waves, we also want to see something when we compare the time of arrival of pulses between pairs of pulsars that are separated by some angle. And what we expect is to have a curve that looks like this black curve here. We expect to see a positive correlation if the pulsars are close together on the sky. If they're around right angle, we expect to see a negative correlation, and that become a positive correlation again. So we can see the data. I don't know if you feel this by eye, but the data itself has a lot of variation from place to place. And the error bars are quite large. So this is really the smoking gun that we're looking for. As we get more data, the expectation, the hope, if this signal is real, is we will get better and better measurements of this curve and see those error bars shrink and everything line up on that black curve. Right now, the evidence is not a smoking gun. It's something that we hope will increase as we collect more data, but it's something that still needs to be processed and thought about. So what might we find? If we measure gravitational waves with pulsar timing arrays, one of the key things, if the gravitational waves come from these supermassive black hole binaries, then we get information about how galaxies interact with each other over cosmological history. But there are more exotic sources of gravitational waves. So one, something called cosmic strings, not to be confused with string theory, but we could have some exotic kind of interesting physics happen in the early universe to produce a new source of gravitational waves. And these measurements, in principle, could actually see this, could detect something like this, or put limits on the possibility of these cosmic strings, the properties of these cosmic strings. One extremely exciting possibility is that we might see gravitational waves from the early universe itself, primordial gravitational waves produced around the Big Bang. This, the kind of basic picture, the consensus picture that we have about the very early universe would tell us this is not very likely, but there are alternatives that might pop up and give us a signal that we would measure the pulsar timing arrays. There's a possibility that this is something, a big mystery in cosmology. We know that there is this matter that's out there that fills up most of the universe. The universe is not made of stuff we're made of. It's made of dark matter. We still don't know what that is. So it's possible that these pulsar timing arrays would give us unique signatures of some strange types of dark matter. And something that's close to my research is thinking about how we can use these measurements to test gravity. These supermassive black hole binaries represent, just like we had with LIGO, a completely new laboratory to ask questions about gravity. And so we have an opportunity here. And a key thing to keep in mind is that every time we probe the universe in a new way, we discover unknown unknowns. So over on the right, I have a little snippet of notes that Galileo took. When he took a telescope, he heard that the telescope was invented in Holland, made his own, and instead of using it to navigate on sea, on boats and so forth, looked up at the sky. And all of a sudden, realized that Jupiter has moons, that the moon has variations, and really transformed our understanding of the universe. So the same thing it has the potential for the same thing to happen here. So to wrap up, just to give you a window into what we have coming up in the next 10 years, what can happen is that this gravitational wave astronomy can significantly grow in the future. Right now, we have these ground-based interferometers telling us something about black holes and neutron stars. This space-based version of these interferometers, LISA, is expected to be launched in 2035. It will give us insights into a whole other class of systems, including potentially some part of the supermassive black hole binaries. And then as time goes on, these pulsar timing arrays will get more and more sensitive, and we're going to see more and more sources. So we're gonna see what's really there. And so maybe in 10 years, we'll have a whole new set of things to talk about in terms of pulsar timing arrays. Thank you very much.
does anyone have any questions? Let's start here. I'm not sure that this is going to be.
I'll repeat the question. So,
No.
hey.
But my understanding of with the rapidly expanding universe that every object is moving farther away from every other object. I wonder how you reconcile that with the colliding galaxies.
That's a great question. So the question is, we know that the universe is expanding, but I also said that galaxies have come together and collide and merge. So that expansion of the universe occurs on larger length scales. And two objects are close enough together and they are bound by their gravitational attraction that overcomes the expansion. So we can have both in the universe.
Hello. Just a point of clarity. The neutron stars that are massive enough to do pulsars are galactic collisions, or are they, say, two stars in a solar in one galaxy like our own that can make a pulsar?
So in the case of just to repeat, so let me make sure I understand the question.
Yeah.
So you're saying, you're asking where these pulsars are formed?
I'm saying when you find a pulsar,
Yep.
I understood you to say
Yep.
that there were a collision of two galaxies
Got it.
rather than two massive stars within one galaxy.
Absolutely. So the two galaxies coming together, that is what produces the potential source of gravitational waves that we would measure with these pulsar timing arrays. So there we have the black holes at the centers of those two galaxies. They then come together and start to put out gravitational waves. The pulsars, they can form by themselves. So they're the end stage of some stars. They are in our galaxy.
But they're not massive enough to become the pulsars? Like, does every collision of two neutron stars cause when you have two neutron stars and they collide, whether they're within one galaxy or two galaxies colliding, can they make a pulsar that you can use in this detection?
I see. So there is, and then so the question is, maybe rephrasing it a little bit. What happens when two pulsars collide? Like, is this something that produces another pulsar that's useful to use? So to rephrase that or to answer it in a slightly different way, we definitely have neutron stars that collide with one another, and that has been measured by LIGO, the gravitational waves produced in that collision, as well as other telescopes see the light from that collision. There's one very famous event that did this. In fact, we found out that much of the gold that we have comes from such collisions throughout the galaxy. After that collision, the mass of that final object is probably so large that it's not going to produce another neutron star. So the neutron stars that we use in a pulsar timing array is the end stage. There's no collision that happens. It's the end stage of stellar evolution, a star that's slightly more massive than our sun.
And next, one more follow-up. The speed of the spin, how relevant is that? I mean, where does that fall in terms of the pulsar you need? And do you need the mass to create, the spin? I mean,
That's a great question.
Is there a pre-mass and a speed?
Right. So the reason that we need, so the question is, I had mentioned that we need pulsars that have a rotation period that's a lot smaller than the general pulsar population. The reason that we need that is because the pulsars that are more rapidly rotating are more stable. So they give us the most stable clocks for us to measure these gravitational waves. I think does that answer your question? Oh, right. So what actually so that's a really good question. A lot of these pulsars that are rapidly rotating started off and may even still have a companion that has some mass transfer, some way of spinning up that pulsar. So there is an evolutionary history to these pulsars that are rapidly rotating that is really interesting in and of itself. Yep.
When discovered the first gravity waves with the LIGO, that was when two black holes merged. That caused the wave. But the more you were talking, it sounds like there's gravity waves going around everywhere. How do you determine, they determine what black holes merge? How do you determine what these black gravity waves are
That's a
doing?
great, so the question is, so, the first detection of gravitational waves, we have an idea, a very detailed idea of what the system looked like as those gravitational waves were being produced. But I also had this image showing a very large volume of the universe and a whole bunch of gravitational waves being produced everywhere. So one way that you distinguish that for something like the interferometers on the Earth is the gravitational waves that were measured in 2015 at an amplitude much larger than anything else. It came washed over the Earth about 7 milliseconds. That was it. So we had this information coming from these black holes, and then that passed over the Earth and went on to possibly be detected by other beings somewhere else in the galaxy. So that is, if the amplitude is large enough, we can hear that above the noise. In the case of these, what we're looking for here, we are looking for something very different. We're not looking for, in the discussion that I had, people are trying to do this as well with pulsar timing arrays, but the first thing we expect to see is this hum, this combination of all of these gravitational waves being produced, and it really is a noise. So it's, the description in that newspaper article about the announced discovery is that this is a hum that we are measuring. And the expectation is after we measure that hum, you can actually see that here in this image, this slightly darker orange is what's called the stochastic background. This is the combination of all of those gravitational waves together. And then we can get down here in this other square, and this is just labeled supermassive binaries. That's the point at which we might actually measure gravitational waves from individual binaries. So there is a distinction between those two sources, those two different types of gravitational waves that we hope to measure.
Do you need the microphone, or can you?
I think I can speak up enough. So I was surprised to learn a few things this evening, that the gravity waves move at the speed of light, and that they have their own spectrum, and that you observe them using an interferometer, which uses light. What I don't understand is understand that you observe these waves. I don't understand what they have to do with gravity, and why it's just not light at a smaller spectrum.
Got it. So that's a great question. So there is, and I was using this analogy, the question is, we have light, which we all are, that I think is incontrovertible. We're using that right now, as I said, to see one another. And there is a spectrum of light. And the question is, what is the difference maybe between gravitational waves and light? Like, could gravitational waves just be another form of light? Is that another way of saying that? So the reason that isn't the case, and maybe I can use this kind of cartoon up here, is that you can think of what actually is happening when we produce gravitational waves as these two objects orbit one another. Those ripples that we're seeing are actually ripples in space-time. Light are fluctuations in electric and magnetic fields. Those are distinguished different physical things. And the properties, so even though it travels, and maybe this is the connection, it does travel at the speed of light. And this might not, I don't know if this will resonate, but if it were up to me, I wouldn't call it the speed of light. I would call it the special speed. And it turns out light travels at this speed and gravitational waves. And the connection, in a real sense, is that they are both describing the motion of massless material. That's a little abusive language. But you have this connection that they both travel at the same speed, but they have very different properties, and they are waves in very different media. It would be like saying sound, which we're using as well. It's also a wave, and it's a very different medium. It's thinking about pressure waves traveling through gas or through a fluid versus electromagnetic waves.
You have a question?
I'll bring in the microphone for you to chat.
Back to your analogy about light photon waves, and then there's photons, right? So are gravity waves transmitted by gravity particles?
Gravitons, yes. That's right. So another way of
Basically detecting gravitons?
that's a more complicated question. So, so the distinction that we're making here is between thinking about light as a classical wave versus a quantum particle. You can make that same distinction for gravitational waves, but in terms of its detection, this is a 100% classical interaction. So there are people who've asked this question. I've looked at the papers, and they are very, for me at least, difficult to parse. Right now, I would say we're just talking about classical gravitational waves. Even though we can take a different perspective and say, yes, they can be described as a collection of gravitons.
Any other questions?
This is a follow-up of a very good question that was asked. What is it about the universe, sir, that would cause these waves to move at the same speed?
It's a great question. So let me see. One way to understand that, and maybe this, so one way to understand that is this statement about photons and gravitons. So I'm not sure that's really going to be useful. They're both massless. They have no mass. And when a particle has no mass, it travels at a very specific speed, the special speed. We happen to call the speed of light, but we didn't need to. It just was an accident of history. Let me see if I can think of another way of describing that. I mean, one other thing I can add is this special speed is an important speed for basic symmetries of our universe. And it turns out that both gravitational waves and light and electromagnetic waves reach the speed limit that's imposed by the symmetry that we have. It's called the Lorentz symmetry. And that's a complicated term. But they both share some really key properties that tells us that they're both going to travel at the same speed. We can also, I mean, just to also say, I mean, in terms of, this is a prediction from general relativity. You can have other theories of gravity that predict these gravitational waves might travel at a different speed. And that's a question we can answer with measurements like those that we're making with pulsar timing arrays. So it doesn't have to be that way, but it's a prediction of the most successful theory of gravity that we have. But there are other theories that would change that prediction.
I have a question. You mentioned that you're examining data that you expected, and also data that you didn't expect. And I mentioned that it might be rubbish, and I was hoping to do something rubbish. And I heard you mentioning satellite, which would then depend all, and maybe due to some expected data that would.
Maybe, yeah. I've heard ideas like that. I wouldn't be able to comment on the specifics of what you read.
But you think it's rubbish?
Well, no, I would say this, that I haven't heard of any additional predictions, and this might just be the lack of my knowledge. When this is posited, it might be some way of attempting to simplify an explanation of something. But it's not necessarily, the key thing would be what's different about what we observe if that were the case versus if it were not. And what we're seeing, I mean, so the data that we've taken with the pulsar timing arrays, nothing has been unexpected in the sense that we have to reach for ideas like we live within a black hole. But there may be a future in which we see things that are unexpected that do require us to revise our theories.
The only reason was because that postulated the reason on black matter is because of this.
Got it. Right. So that, I mean, there are a lot of ideas. This dark matter, the fact that we know that it's out there, but we don't know what it is, has generated a lot of creative explanations. And for what it's worth, my money is on the fact that we will identify what it is, and it's not going to require something like this. But, well, maybe not. I mean, it's still, there are interesting ideas that don't need to be at the forefront of what we're looking at that might come up later. But, yeah.
So my question is, if PTAs are able to detect gravitational waves, and gravitational waves are theoretically related to gravitons somehow. How could PTAs help reconcile quantum and the standard model?
It's a great question. So, I mean, I unfortunately, though, I come back to what I had said before. There is nothing in the detection of gravitational waves using either pulsar timing arrays or the interferometers that would give us, to the best of my knowledge, and at least the kind of standard expectation, any new insights into the connection between quantum and gravity. That's not to say there aren't ideas out there that I'm not familiar with, but it's not kind of the mainstream. It really is the interest. The expectation is that we're going to see a signal that comes from these supermassive black holes, and we have a framework to explain all of that. Again, if we see something that we don't expect, it's possible that there's something else going on, and you can be sure that there will be a lot of people trying to figure that out.
The universe was opaque to electromagnetic waves before recombination. Were the primordial gravitational waves that you mentioned, were those originating before recombination?
That's a great question. So just to rephrase, so in the history of the universe, there was a moment in the past when the universe went from being opaque to light to being transparent. That's actually the origin of what we measured, the afterglow of the Big Bang, the cosmic microwave background. One of the most exciting things about gravitational waves is that, so we have a kind of hard cutoff in terms of direct information about the universe. We know what it was doing after about 400,000 years after the Big Bang. That's when the universe went from opaque to transparent. Gravitational waves, because it's gravity, they don't have this effect, at least not unless you go super, super far back. So gravitational waves have the potential to carry information about much, much earlier times, direct information about what the universe was doing much earlier times. Fractions of a fraction of a fraction of a second after the singularity, initial singularity. So it's a great point. Weakness of gravity is a wonderful thing when you think about it that way. It potentially gives us information that we would otherwise not be able to get.
And were those primordial gravitational waves, they originate before recombination?
They did, yes. So the expectation in the standard kind of consensus model is that they originated during a phase of the universe called inflation. The universe was rapidly expanding during this time, and quantum fluctuations produced gravitational waves that, in principle, we could see. The most likely place we will see that is in the cosmic microwave background polarization. So that's where we expect to potentially see it. We would get information about very, very early universe if we were to see that.
Yes.
I'm struck by your 2018 to 2030 cartoons there, and it's probably related to your correlation versus angular. So how often are these supermassive binaries combining, and how many events do you anticipate there to get the curves where you get to the ideal error bars on the earlier chart?
That's a great question. So right, so these kind of shaded regions here come from models of the sources themselves, and so there are assumptions that go into that. I don't have on the tip of my mind the exact numbers of the rates of mergers, but there is a whole set of ingredients that go into making those predictions. So one, I would say very exciting possibility is that these predictions are wrong, that we have something wrong with those ingredients. And it's possible that we increase our sensitivity. So as this curve goes down, getting more and more sensitive to gravitational waves, if we still don't see anything significant, that would cause us to have to go back and revisit a whole bunch of things, including the possibility that we have ideas about how galaxies evolve over time has to be rethought.
All right. If curiosity has been satiated, let's go ahead and thank Tristan. And